Efficient Frontier Scenarios Multi-Security Case 2. In this video, we'll discuss the shape of efficient frontier with multi-securities and introducing riskless or risk-free instrument. We'll discuss three cases. First, efficient frontier with riskless lending and borrowing. Then only riskless lending is allowed, not borrowing. And then riskless lending and borrowing at different rates. As we can see, we gradually move in a step-by-step manner towards a more realistic assumption of different riskless lending and borrowing rates. Up until this point, we were focusing on risky securities. The addition of riskless securities considerably simplifies the analysis, as we'll see now. Here, we are assuming the same rate for borrowing and lending, that is RF, in the first case, which is this RF, same lending and borrowing interest rate. Because the return on these securities is certain, whether it is borrowing or lending, practically this does not happen. Borrowing is often at higher rates than lending. However, for analysis purposes, let us consider the same lending and borrowing rates for now. Now here the intercept is RF. This risk-free rate becomes our intercept. And if you pick randomly any point A on this efficient frontier, then the slope of this line would be RA bar, which is my expected return on RA, minus RF upon sigma A, which is the standard deviation of or risk of security A. This is often referred to as Sharpe ratio also. This RA bar minus RF upon sigma A. RA bar is the expected return on security A and RF is the risk-free rate. The point on the line that is to the left of A, these set of points left to the A till RF, these are the combination of lending at risk-free rate, that means investment in risk-free rate, and investing in portfolio. So a mixture of investment in RF and RA would fall on this line. Conversely, the point on the line that are to the right of A, that means on this side, these are called a combination of borrowing at RF and investing original wealth as well as the borrowed amount in A to result in a position that is on the right of the A on this line segment, and therefore these are called the borrowing segment of the line. However, here we chose the portfolio A randomly with only criteria that it is on the efficient frontier. There may be other portfolios like A, B or G, and the resulting graph may look like this, as we have seen here, like this and like this. Now we have three lines indicating the risk return profile corresponding to three portfolios A, B and G here. These lines extend the possibility region. For example, with line B, our possibility region is like this. With A, our possibility region is like this. And investors can hold portfolios on these lines joining risk-free rate and points A, B and G. Now the question is, which portfolio is better for us? There appear to be an obvious question. For example, if you look at the points on line RF to B, this RF to B, it offers the higher returns than as corresponding to RF to A. So RF to B offers higher return as corresponding to RF to A for a given level of, for any given level of risk, as we can see here. For any given level of risk, RF to B offers a higher return. Similarly, the points on RF to G offer higher returns than those on RF to B. So this means as we are rotating this line, in the counterclock direction, we are making it steeper and steeper. It suggests that the concept of tangency would indicate the highest we can rotate is up to the point of tangency, which is here point G, as shown here. At this point, the line passing from RF attains the highest slope. Remember that Sharpe ratio, RG bar minus RF upon sigma G, the Sharpe ratio. This slope or the ratio would be highest when the point is tangency point, touching the efficient frontier at tangency point. So if the line is further rotated, then there are no portfolios that are in the feasibility region or on the efficient frontier. Therefore, this line RF to G would offer the highest return for any given level of risk as compared to any combination of risk-free asset and investment on any point of this efficient frontier. Therefore, theoretically, all the investors, whether riskless or less risk preferring or more risk preferring, they should all hold this portfolio G. Now, those investors that are more risk averse would invest some of the amount in risk-free rate. Those who are risk averse would invest some amount here on RF and some amount in their portfolio G, so that they are on this segment RFG. This is called the lending segment. Similarly, those investors who are more risk preferring, who would like to take more risk, their portfolio would lie on the segment called borrowing, which is on the right side of G. So they will borrow at this risk-free rate and invest not only their original wealth but this additional borrowed amount also in the portfolio G. So this is one of the very important tenets of portfolio problem. Here, even if you do not know the investor's risk profile, whether he is more risk preferring or less risk preferring, once you identify the portfolio G, you can draw a risk return profile for all the optimum portfolios. This is also sometimes called separation theorem or two mutual fund theorem, because we separate the risk profile of the investor from the investment, because we select only two assets. First, a risk-free asset, and second, the portfolio of assets, risky assets called the market portfolio, this portfolio G. And then for all the investors, some combination of RF and G on the lending segment or borrowing at RF and investing in G would create the desired optimum portfolio depending upon their risk preferences. Now let us discuss a special case where only riskless lending is allowed and borrowing is not allowed. This is a slightly more previous practical case than our previous case, as generally lending at, let's say, government fixed deposits or various other instruments are available at risk-free lending at significantly lower rates. However, borrowing at such lower rates is not available. So once we put this constraint, the segment on the line joining RF to G, this segment RF to G called borrowing is not available. So we have now only lending, this RF to G available, but not on the right side, which was the borrowing segment, that is not available to investors. So the now efficient frontier would look something like figure here, RF to G on the straight line, and then from G onwards, this is the efficient frontier. So it is like RFGH. GH is on the right side of RFG, which was part of efficient frontier in the absence of risk-free asset on the right of G. H here is the point of maximum return. In effect, the efficient frontier becomes RFGH. The investment profile of risk-averse investors who are placing some amount in risk-free instrument and some in G, the lending segment, will not change. Only the risk-taking investors will not be able to borrow at RF. They will invest in portfolio on the segment GH. The portfolios on this GH segment are relatively riskier than portfolios on RFG, but these portfolios also offer the higher returns possible at any given risk. So they are offering highest return for any given risk levels. Also, please note that in this case, we need to only identify two risky portfolios, G and H. So once you identify G and H, all the combinations of G and H would lie in between on this curve segment GH. Since all the portfolios on curve joining G and H can be obtained by combining G and H. Lastly, we'll discuss a special case where the riskless lending and borrowing is allowed at different rate. This is a very practical case which we encounter in daily lives. The interest rate at which we borrow is usually much higher than the interest rate at which we invest. For example, you can borrow probably here at RF and invest at RF and borrow at RF dash. RF dash is higher than RF. So the investment profiles for this case is shown here. Now the borrowing at RF dash, which is higher than the lending rate RF, and again for the risk averse investor, the risk return profile remains unchanged. However, the region of borrowing is modified due to higher risk free rate. So the region of borrowing is here. This is the region for borrowing for him, a higher region. Let us say that with the new borrowing rate, the point of tangency is H. So for this RF dash, the point of tangency is H. For the lower rate, the point of tangency is G. So the risk-taking investor have the efficient frontier as the risk portfolios lie between GH curve. So he can invest on GH curve. And after H, the tangent line that joins RF dash to H. So he has this GH curve and then from H onwards. So RF dash H line which extend from this point H. So for risk taking investor, it will be something like this. So this is GH and then line extending, R dash F line extended, R dash F H line extended beyond point H. So effectively your new investment frontier becomes starting from RF to G. So those who are less risk taking, they can probably invest some amount in RF and some amount in G and obtain a portfolio on this in lending segment RFG. And then if you are more risk taking, then your portfolio extend beyond G to H and then H onwards from H to further on this line segment RF dash, which is extended. So your RF, G, H and beyond this line is your complete segment. For those who are less risk taking, they will invest partially in RF and some amount in G, so they will obtain a portion on this RFG portion, they will invest, and those who are more risk taking, they will invest beyond G to H on this curvature and then straight line, which is R dash F H extended. To summarize, in this video, we introduce risk-free or riskless instrument with efficient frontier. We discuss three cases. First, with same riskless lending and borrowing rates. Second, unlimited riskless lending but no riskless borrowing. And third, the most practical case that is different risk-free lending and borrowing rates, where risk-free borrowing is at higher rate while risk-free lending is at lower rates. We found that when risk-free asset is introduced, one can find an optimum portfolio which can be available or made available to all the investors irrespective of their choices. For example, we found there was a portfolio G when riskless lending and borrowing rates were same, and a combination of this portfolio G along with risk-free rate can be offered to all the investors irrespective of their choices. Those investors that are less risk-taking would prefer to invest some amount in the risk-free rate and some amount in the risky asset, while those who are more risk-taking, they would like to borrow at risk-free rate and invest further their original wealth as well as additional borrowed amount in the risky portfolio. So these two segments are called lending and borrowing segment respectively. Lending segment for less risk-taking investor who is investing in risk-free asset as well as risky asset, while borrowing segment for investors who are borrowing at risk-free rate and invest the borrowed amount and overall wealth into this risky portfolio to obtain a position on borrowing segment. In this video, we'll talk about minimum variance portfolio and some of its interesting properties. In the absence of short sales, 2 points become extremely important on the efficient frontier. First, the portfolio with maximum return, and second, the global minimum variance portfolio. In the absence of short sales, these portfolios define the two extreme ends of the efficient frontier. While it is easy to understand that maximum return portfolio will be the security in the portfolio that offers the maximum return, since the returns are simply the weighted average of returns. The same is not the case with the global minimum variance portfolio. This portfolio is often expected to be different from the security with minimum risk in the portfolio. How do we compute this portfolio? We already know the generic formula for portfolio risk as shown here. The formula is simply sigma p is equal to xa square sigma a square plus sigma b square xb square plus 2 times xa b rho ab sigma b whole to the power 1 by 2. This is for two security case. Now, this formula we can simply compute in order to compute the minima, we need to simply differentiate this expression sigma p, that is d of sigma p. We'll not go into the detailed exposition, but we need to differentiate this expression with respect to dxa, and in order to obtain the minima, we need to set this derivative equal to 0 and solve for xa. Solving for xa, we'll get something like this, a simple expression like this, which is xa equal to sigma b square minus rho ab into sigma b upon sigma a plus square plus sigma b square minus 2 times rho ab into sigma b, where rho ab is the correlation between securities A and B, sigma is the standard deviation of security A, sigma b is the standard deviation of security B, which expression is given by question 3 here. Now let us consider a simple example here. We have been given two securities, stock A and stock B. Stock A has an expected return of 14% and a standard deviation, that is risk, of 6%. Similarly, stock B has expected return of 8% and standard deviation, that is risk of 3%. Now, if we assume that the correlation between these two stocks is 0 and we would want to find the minimum variance portfolio for this particular correlation, we need to solve for this expression, and putting rho AB equal to 0, we are left with this term, and given that the risk is for B is 3% and A is 6%, we get this XA is equal to 0.2. Since we already know that XA plus XB equal to 1, we get XB equal to 0.8, and therefore we can compute now sigma P with the expression known to us. Sigma P becomes 0.2 square into 6 square plus 0.8 square into 3 square, which is simply nothing but XA square sigma A square plus XB square sigma B square raised to the power by 2, which is 2.68%. So this is the risk of minimum variance portfolio here. Now let us assume a correlation of 0.5 and then try to compute this expression. Putting correlation as 0.5, we find that XA equal to 0. What is the implication here? Since no combination of securities A and B has less risk than the security B itself, so the global minimum variance portfolio is security B itself. And that is the reason when we compute global minimum variance portfolio here, we get X equal to 0, which means XB equal to simply 1, which is security B itself. That also means that for any correlation higher than 0.5, the global minimum variance portfolio will be obtained for XAs that are less than 0. Or in the absence of short selling, for all practical purposes, we get X equal to 0 and XB equal to 1. That means for any correlation that are more than 0.5, the minimum variance portfolio in the absence of short selling will be XB equal to 1 itself. That is security B will remain the global minimum variance portfolio. Now let us assume a correlation of 1 exactly, rho AB equal to 1, and then try to solve this. In that case, when we do that, we find XA is less than 0. In the absence of short selling, which is not a practical thing here, and therefore the limiting constraint that any weight cannot be equal to 0, this gives us X equal to 0 because we are assuming that XA cannot be less than 0. So we are assuming a correlation of -1, and if we assume a correlation of -1, we compute this expression which works out to be XA equal to 1 by 3 and XB equal to 2 by 3. Solving for this, we get XB equal to 0, which is nothing but XA sigma A minus XB sigma B, or WA sigma A, WB sigma B, where WA or XAs are the proportionate amounts invested in security A and B. Now this is a special case where rho AB, or correlation between the securities, is equal to -1. However, that is less of a practical case because perfect negative correlations of -1 are rarely observed over long horizons. However, still this is a theoretically important case. Why? Because in this case, we are able to obtain complete diversification. That is, the complete portfolio risk has become equal to 0. So this is a theoretically interesting case where all the risk of the security or portfolio has been diversified. To summarize, in this video, we computed the formula for minimum variance portfolio. We also computed, and through examples, we understood different values of this minimum variance portfolio risk for different values of correlation. We also found that at a particular correlation of -1, the overall portfolio risk can be made 0, and in that case, global minimum variance portfolio risk will become 0 as well. We also noted that it is not necessary, unlike returns where the maximum return or minimum returns are equal to simply the maximum minimum return security in the portfolio. The minimum risk portfolio can have even lower risk than the security in the portfolio with minimum risk. Introduction to risk-free lending and borrowing, part 1. Till now, we have touched upon the use of risk-free instrument in construction of efficient frontier in a more cursory manner. In this video, we'll explore the application of risk-free instrument in efficient frontier construction in more detail. Let us first start by introducing the risk-free lending and borrowing at the same interest rate, that is RF. However, is it practical to assume that risk-free lending and borrowing would be available at the same rate? What are the challenges with this assumption? For example, can you borrow from a government bank like SBI or lend or create fixed deposit with the same bank at the same rate? Is it possible? While this assumption has several challenges, still this assumption has a lot of important implications when it comes to portfolio construction and understanding the efficient frontier. Let us start by assuming a large number of stocks that are used to construct a feasible region of possibilities. You invest in a number of stocks to construct the portfolio, and the feasible region that you will obtain will something like this, the green region obtained here. And you will obtain a very wide selection of risk and return profiles in the form of this feasible region. Now, in this feasible region, you would want to go up in order to increase your expected return for a given level of risk, or you would want to go to left to decrease the risk for a given level of return. And as you keep on doing that, you will obtain this efficient frontier or best set of portfolios that offer you best or optimum combination of risk and return. Mathematically, in order to solve this, you need quadratic programming, This is a sort of capital rationing problem where you have a capital constraint. For example, you may have a capital constraint like xi equal to 1, where xi's are proportionate amounts invested in different securities. And then using this constraint, you would like to solve or maximize your return for a given amount of risk with this capital rationing problem. And you can solve this with quadratic programming. You would need some computer program or software. There are a lot of easily available software packages that can do this. However, addition of riskless securities can considerably simplify our analysis. For example, consider two investments, one in a portfolio of asset A, this risky stock, and another a risk-free asset may be here. When you have this, then your possibilities improve considerably. There are two segments to this investment. One, if you invest some amount in RF and some amount in A, you obtain what is called lending segment in this region. Generally, a person who is less risk averse would be standing here. Or you can borrow at RF, because we assume that borrowing and lending risk-free rate are same. So you can borrow at RF, invest your own wealth along with any additional borrowed amount in asset A to obtain a position on this borrowing segment. This is precisely the equation of a straight line like y equal to mx plus c, which passes through 2 points. First point is this point A with the expected return of RA bar and risk for sigma A. Another point which is risk-free asset with the expected return of RF and risk of 0 or standard deviation of 0. Let us assume that amount fraction x is placed in the portfolio A, XA. Let's call it x or x. And then therefore remaining 1 minus x amount, because of capital constraint, the summation of XA plus XF should be equal to 1, where XF is the amount invested in risk-free asset, though they should be equal to 1. So the amount invested in risk-free asset is 1 minus x. And therefore the expected return on this portfolio RP is equal to simply x into RA bar plus 1 minus x into RF. RF is the certain return on risk-free instrument. Again, we can also compute the risk of this portfolio sigma p square very simply, x square sigma a square plus 1 minus x square sigma f square plus 2x into 1 minus x rho f sigma a sigma f. But please remember here, the sigma f equal to 0 because there is no risk with the risk-free instrument, and therefore the amount is simply say x square sigma a square. And if we can assume that, then assuming that sigma f equal to 0, we are left with the portfolio risk, a very considerably simplified expression. Because of this introduction of risk-free instrument, we have only this expression as a portfolio risk, sigma p equal to sigma x a sigma. And we already know that RP can be demonstrated or described with this expression. Using these two, equation 1 and 2, we can further simplify this expression in the form of RP bar equal to RF plus RA bar minus RF bar upon sigma a into sigma p. Now, this is a very simplified form of expression of portfolio expected return and risk. And this equation is precisely the straight line that passes through all the combinations of risk-free lending and borrowing with portfolio F. So if you remember, this was the efficient frontier, and any point A if you have picked here, then this would represent all the points on this line. This expression would provide you with the expected return and risk relationship which passes through this line. All the points on this line will be described by this equation. To summarize, in this video, we saw that introduction of risk-free instrument where risk-free lending and borrowing can be done at the same rate considerably simplifies the analysis of efficient frontier, and we obtain a very simple expression of relationship between expected return RP bar and risk of the portfolio. This is obtained because the risk of the risk-free instrument, that is sigma f, is equal to 0, and because of that assumption we are able to obtain this very simple expression of expected return and risk on the portfolio. This is a more generic expression. Introduction to risk-free lending and borrowing part 2. In this video, we'll try to find whether there is a special case or optimum portfolio with the presence of risk-free lending and borrowing that is dominating or dominant position as compared to all the other portfolios or risky assets. Please remember, as we have this opportunity to invest in risk-free asset as we saw in the previous video, we can take any position on this efficient frontier. We saw that this brown line represents the most set of efficient portfolios or efficient frontier. And now that we have this risk-free asset, I can pick and choose any point on this efficient frontier and combine it with my risky portfolio and find a number of set of opportunities, a very specific set of portfolios that depend upon the risk-free rate and the position that we are taking on this. Let us find out if there is a particular portfolio on this efficient frontier that offers us the best set of combinations of risk return profiles. It would be easy to understand that if I keep on moving on the counterclockwise, I would find the steepest line to be at the tangency point. Let's call this tangency point as S. Please note, if this tangent line from RF to S is drawn, let's put it with the red line, this tangency line. This line will be the steepest line from RF to this efficient frontier. The slope of this line can be easily defined as RS minus RF upon sigma P, where RS is the expected return on security S, RF is the return on risk-free instrument, and sigma P is the risk of the portfolio, that is S. Now, given the fact that this slope is the highest, this is the steepest line, we can easily say that this line or this position S offers maximum expected return for a given level of risk, and that is true for all the points on this line, that they offer for a given level of risk highest amount of return possible as compared to any other point on this efficient frontier. For example, if I draw another line like this for a point, let's say A, all the positions on this line would be a better combination of risk return, that means higher return per unit of risk as compared to any on this line which is joining RF to A. Often this ratio is called, this ratio RS minus RF upon sigma P is a very important ratio called Sharpe ratio to measure the performance of a portfolio. Now we have obtained a particular portfolio or position which in combination with this risk-free instrument offers us the best or optimum set of positions, or a new efficient frontier in fact. So this we can call as a new efficient frontier which is become available to us because of this risk-free rate. There are two particular segments on this new efficient frontier that are very important to us. One is called lending or investing, this one, and other is called borrowing. So this lending segment is preferred by investors with low risk preference, while this borrowing segment is preferred by investors with high risk preference. What do I mean by this? So those that are less risk averse, they would be borrowing at RF and investing their own wealth along with this borrowed amount in S to obtain a position on this borrowing segment which extend from S and beyond on this straight line. While those who are high risk averse and do not prefer risk much, they would invest partially their wealth in RF and partially in S to obtain a position on this segment RFS, which is called lending or investing. Now please remember, this kind of position on lending and borrowing segment is freely available to all, and if this portfolio S is known with certainty, then everybody would be holding this portfolio S. Nobody would hold any other portfolio but some proportion of investment in S and some proportion of investment or borrowing in RF. And therefore, since everybody is holding these two portfolios only, the only set of risky assets are held are that in portfolio S. And therefore, this portfolio S is also often referred to as market portfolio, sometimes denoted by M or sometimes by S. This is a market portfolio which is held by everybody. Why we are making this assumption that financial markets are often considered to be very efficient and competitive. So there's no reason for us to believe that anybody or somebody may have a particular advantageous information over long times. That means everybody will have some similar information and all of them will want to hold the same market portfolio M or what we call S. And therefore the job of investment manager becomes very easy, is to find this market portfolio. Once he has identified this market portfolio of common stocks, he need to mix it with RF depending upon the risk preference of individuals. Those who are risk averse, more risk averse, for them some investment in RF and some investment in S. While those who are more risk taking, some borrowing at RF and the borrowed amount plus own wealth can be invested in S to obtain a position on this borrowing segment. So mixing this market portfolio or this portfolio of S along with risk-free asset in different combination can generate various combinations of portfolios that may suit the taste and risk preferences of different profile of investors. And that is why this is often referred to as two-fund theorem or separation theorem. That means the decision to select this portfolio S is independent of investors' risk preference and risk profile. This is a very important result. So whether investors are risk-taking lions or risk-fearing chickens, they can be provided their suitable instrument just by mixing this one portfolio S along with the risk-free instrument. To summarize, in this video, we saw that when the risk-free instrument is available, one particular portfolio, which is the tangency portfolio, becomes the optimum position for all individual investors, and therefore a fund manager can mix this particular optimum portfolio with a risk-free instrument to provide various combinations of portfolios. This includes portfolios on lending segment for those who are more risk averse, and portfolios on borrowing segment by borrowing at RF and investing all in risky asset to those who are more risk taking. And therefore, the fund manager can separate the decision of investing from the risk profile of individual investors. This is often referred to as separation theorem or two-fund theorem. Introduction to risk-free lending and borrowing, part 3. In the previous videos, we have understood the introduction of risk-free lending and borrowing can simplify the analysis considerably, and we find an optimum portfolio that is suitable for all. In this video, we'll understand the implications of that optimum portfolio with the help of simple numerical examples. Suppose the market portfolio that you have identified, the best optimum portfolio S, offers 15% expected return and a standard deviation of 16%. Also, the risk-free instrument available to you offers you a 5% return of lending and borrowing with a standard deviation or risk of 0. Now, you are a risk-averse investor, therefore you would like to invest 50% of your money into RF, which is risk-free, and remaining 50% into a portfolio S. Now, what does your portfolio look like? Let us try to find out the profile of your investment with the help of following equations of risk and return. We have seen that the risk of our portfolio would be sigma p equal to x times sigma a, while the expected return of the portfolio is x times RA bar plus 1 minus x into RF. Now let us punch in some values here. So given that our investment is 50-50% into risk-free instrument and risky portfolio, our resulting expression becomes RF into 0.5 plus RS into 0.5, which is equal to 10%. 5% into 0.5 plus 15% into 0.5, which is 10%. The standard deviation of our portfolio sigma p is equal to 0.5 into 16%, which is 8%. And therefore, at this stage, we are standing on that lending segment of portfolio. If this is the tangency portfolio S, this is RF, then right now we are standing somewhere in the mid of this, which offers us an expected return of 10% and risk of 8%. So this is midway between RF and S. Now consider another investor who is more risk taking in his approach. This risk taking investor would like to rather borrow at RF almost 100%, which is equal to his initial wealth, and invest the total amount, that is 100% of borrowed money plus 200% of his plus 100% of initial wealth, that is overall 200% in this market portfolio S. And therefore we can easily compute the risk return profile of this investor in the following manner. First, his return will be RF into -1. This -1 represents the 100% borrowing, plus RS into 2, which represents 200% investment in market portfolio. The resulting profile becomes 5% into -1 plus 15% into 2, which is 25%. Now this is quite a large return, expected return that he's getting from his portfolio, a very high return. But at the same time, his risk is 2 times 16%, which is 32%. So while this investor has extended his possibilities and he's obtaining a very high amount of expected return, he's standing on the borrowing segment and his risk has also increased considerably. So his position, if this is the tangency portfolio S, this is RF, then his position is almost here. So while he's getting that higher expected return of 25%, at the same time he's also facing a risk of 32% standard deviation. So we saw whether one is a risk fearful chicken or less risk taking person, or a risky lion, that means a more risk taking person. Both of them will prefer to invest in market portfolio than any other combinations available on the efficient frontiers. This tangency portfolio, what we are calling as market portfolio, and therefore this market portfolio is the best efficient portfolio from all the entire set of investors. For all the investors, this is the best portfolio. And identifying this best portfolio is quite easy. We need to draw a tangent line from the risk-free instrument RF to the efficient portfolio, the original efficient portfolios that we identified. These efficient portfolios, we need to draw a tangent line from this risk-free instrument, and this tangent line will give us that market portfolio. This portfolio offers us the highest risk premium, that means highest value of this Sharpe ratio, which is RS minus RF upon sigma p, or the slope, this Sharpe ratio or the slope or the amount of risk premium per unit of risk is offered by this market portfolio is highest, which represents the slope of this line. To summarize, with these numericals, we saw whether an individual is risk preferring person or less risk preferring person. One particular portfolio, which is the market portfolio or tangency portfolio, is the most preferred for all of us. And therefore, a combination of this market portfolio with that risk-free instrument provides us with our required portfolio with the best combinations of risk return. The slope of this portfolio or the per unit of risk premium for a given unit amount of risk is best across all the set of portfolios available to us on the efficient frontier. And therefore, this market portfolio or optimum portfolio helps us solve the portfolio problem. Market risk and beta. In this video, we'll talk about market risk and a very important measure of market risk, which is beta, which is the sensitivity of a security to market risk. With the help of a simple example, we'll also try to understand the computation of beta. Usually, market risk is associated with a well-diversified portfolio. This is so because for a well-diversified portfolio, the diversifiable or stock-specific risk is eliminated and only it is the systematic non-diversifiable market risk that matters. For example, a portfolio like Nifty 50 or NYSE index, S&P 500. For such portfolios, only market risk matters. So if a sufficiently large amount of securities are added to a portfolio, the only risk that matters is the non-diversifiable systematic or market risk. What is this market risk? Remember the diagram that we saw earlier. So market risk is the bedrock of risk. There are two components. One is idiosyncratic stock specific risk, let's call it SP, and market risk, which is driven by the correlation across securities. Now, as you keep on adding securities, 0, 1, 2, 3, after sufficiently large number of securities are added to the portfolio, then this stock specific risk eliminated and it tends to go to very close to zero. Even with 30-50 securities, it can be completely eliminated. While the market risk is not eliminated with this diversification of adding more securities, and it sustains. However, it is important to know when a new security is added to a portfolio, what is the contribution of this security to the portfolio? And this contribution of the security to a portfolio is determined by the correlation of that security with the market portfolio. Market portfolio is a portfolio of stocks that carries sufficiently large number of stocks from the market that represents the market and eliminates most of the diversifiable risk. This correlation between that security and market portfolio is often measured through beta I. This is called beta of the stock or sensitivity of the security to the market portfolio. For example, if the market moves by 1% up and security moves by 1.5% up, then in that case we will say that the beta of the security is 1.5. Or if market moves by 1% or a particular amount and security moves by exactly the same percentage, let's say in this case 1%, then it is said that security has a beta of 1 and it has the same risk as that of the market. Another interesting case is that a security is insensitive to market. Although it is more of a theoretical case, generally securities move to some extent, some may large, some may small, but they definitely move when market shifts. But theoretically, if a security is not at all sensitive to market and therefore whether markets move up or down, it does not move, then we say that beta of that security is equal to 0 and that security does not have any market risk or systematic risk. One good example of this would be government securities, because government securities are risk-free and they are not affected by the market risk, or they do not move with the market. So essentially, in summary, this beta represents the sensitivity of the security to market movements, and therefore this beta is a good measure of security's contribution to portfolio risk, because it is not eliminated. When you add the security in the market portfolio, this risk is not eliminated. What about the risk of a portfolio or beta of a portfolio? Mathematically, beta of a portfolio is weighted average of betas of individual securities. For example, if you have a n stock portfolio, 1 to n, then if individual betas are beta 1, beta 2, beta 3 and so on up till beta n, where proportionate amounts invested in these securities are W1, W2 and so on up till Wn, then the beta of the portfolio can be simply written as beta P equal to W1 beta 1, W2 beta 2 and so on up till Wn beta n. So summation Wi beta I is the beta of the portfolio. This is the beta of the portfolio. For example, if you observe that the market has a standard deviation of 20% and you construct a portfolio which has a beta of 1.5, then the standard deviation of this portfolio would be 30%, which is 1.5 times 20%. So in summary, the beta of portfolio is simply the weighted average of betas of individual securities. Now, how to mathematically compute betas of a security or a portfolio? So beta of a security or portfolio I is simply the ratio between covariance of that security and market, which is sigma IM, divided by variance of market. So this formula represents the mathematical computation. It comes from the regression model, as we'll see shortly, but this is the ratio of covariance between the security and market divided by the variance of the market. Now, how to compute betas in real life from the given data? So security returns are regressed on market returns. For example, a security I would be regressed on a market returns, where market can be proxied like indices such as Nifty or NYSE. And in this kind of regression model, the slope of the variable market, that is Nifty or NYSE, is called beta. This computation of beta requires us to understand the regression analysis a little bit briefly. So the model that we are running is y equal to alpha plus beta times x, where y is the return on the security I. It can be any security or a portfolio. And alpha is the constant intercept term here, and beta is the slope of market variable x. Now mathematically, in a regression model, it works like this. You have scatter plot where you have different return observations plotted along two axes, x and y, where x is the security return, y is the market return. So if these blue points represent those observations, then you fit a line using ordinary least square method. Notice, as the OLS works, you try to minimize this error, this difference, sum of squares of these errors. These are error terms, EIs. The fitted line, perpendicular between fitted line and the observed point, you take all these errors, EIs, and you try to minimize the summation of square of these error terms. That is, you try to minimize the summation of these error terms, and when you minimize, in that process you obtain the fitted coefficients. You obtain these alphas and betas by fitting this line, which has minimum squared residuals, and this line is called OLS fit, ordinarily least square fit, ordinary least square fit model. In this process, the coefficient beta you get is represented by this formula mathematically, which when translated to our context or our background of market risk becomes sigma IM, which is the covariance between the security and market divided by variance of market, sigma square m. So this is the formula for beta, where it comes from using regression analysis when an OLS ordinary least square line is fit between security returns and market risk returns regression. Let us do a simple numerical example here to understand this process. Let's say we have these return observations given to us, and market return observations and security return observations for security 1, let's call them R1, and RM for market returns. First, we'll compute the difference between or deviations from mean, like RM minus RM bar. So the mean of RM is 0.3, so minus 1 minus 0.3 is 1 minus 1.3, and similarly we'll compute deviations for all the observations. Same goes for the security returns. Its average or mean is 3.7. So for example, first observation 3.6 minus 3.7, which is minus 0.1, and similarly we'll compute the deviations for all the points. Then we'll also compute the standard deviation of market, which is deviation squares. For example, square of this term, deviation squares, and then summation of all these deviations will be averaged out by dividing them with the total number of observations, which is 10 here. So we get this 63.01, which is the summation of this upon n. Similarly, we'll compute these multiples, RM minus RM bar into R1 minus R1 bar to get this number, and then multiply this to get this number, and this multiplied by this to get this number, and so on. We'll get all the 10 R1 minus R1 bar into RM minus RM bar, and then divided by the total number of observations, that it's 10, to get this number. Now the ratio of this is our covariance between security and market, and this is our standard variance of market. If we divide the sigma IM by sigma m square, we get the beta measure, that is 0.08, that is 5.04 divided by 63.01, we'll get 0.08, which is our measure of beta of the security or portfolio. To summarize, in this video we understood the concept of beta, which is the sensitivity of security to the market movements and a very important measure of a risk of that security. This represents the sensitivity to the security to the market movements and therefore the contribution of the security to the portfolio risk. We also understood that this beta can be calculated by regressing the security returns on market returns, and the slope coefficient on the market variable is this beta. Mathematically, this is the ratio between covariance between security and market divided by variance of market. This is our beta for that security or portfolio. To summarize this lesson, for a portfolio with a large number of securities, only systematic or market risk that is relevant. Idiosyncratic stock-specific risk is eliminated due to diversification. When two securities are perfectly correlated, that is their correlation equal to 1, no diversification is achieved. When two securities are perfectly negatively correlated, maximum diversification is achieved. As we keep on adding more and more securities, the region of all possible risk return scenarios is obtained, which is often called feasible region. On this feasible region, we would like to go up, that is increase the expected returns, and go to the left, that is decrease the risk. When short selling is not allowed, a set of best efficient portfolios from minimum variance portfolio to maximum return portfolio are obtained that dominate all other risk return profiles and often referred to as efficient frontier. When short selling is allowed, an extended feasible region is obtained. The efficient frontier is also extended to the top right. In the presence of risk-free security, a new efficient frontier is obtained, which is a tangent line joining risk-free security to the tangency point. On this new efficient frontier, the line segment toward the left of the tangency point is called the lending segment, which is a mix of investment into risk-free security and tangency portfolio. The line segment towards the right of the tangency point is called the borrowing segment, that is borrowing at the risk-free rate and investing the complete amount into the tangency portfolio.